Hello everyone. Let's continue our discussion of derivatives by looking at a couple of examples. Here we're asked to determine if f prime of 0, if f of x is equal to absolute value of x. Now f of x is equal to absolute value of x means that f prime of x will be equal to the limit as h approaches 0 of x plus h, the absolute value, minus absolute value of x all over h. Notice that we cannot expand or cancel anything much here, so let's go ahead and plug in our zeros for x. So f prime of 0 will be equal to the limit as h approaches 0, absolute value of 0 plus h minus absolute value all over h. It's going to be equal to the limit as h approaches 0 of the absolute value of h over h. Again, we cannot just cancel the h's because we're dealing with signs. We're talking about absolute value, positive and negative signs. Let's talk about what the absolute value of h means. Absolute value of h means that if h is positive, then our answer will be h. Or if h is greater than or equal to 0, then our answer will be h. If h is less than 0, the absolute value of h corresponds to negative h. So let's look at the limit as we approach 0 from the left side and from the right side. The limit as h approaches 0 from the left, the absolute value of h over h will become the limit as h approaches 0 from the left, negative h over h, that will be equal to negative 1. Here we can cancel. The limit as h approaches 0 from the right, that's absolute value of h over h again, that is equal to the limit as x approaches 0 from the right, h over h, that is equal to 1. Notice for the absolute value function, then the slope as we approach 0 from the left is negative 1, as we approach 0 from the right is 1. Because these two slopes, or because these two limits, because these two secant lines, tangent lines, as we approach from the left and right are different, limits are different from the left and right. From the left it's negative 1, from the right it is 1. Therefore, the limit as h approaches 0 itself does not exist. Let's look at another problem, an application problem. A cylinder has a height of 30 centimeters and a radius r centimeters. Determine the instantaneous rate of change of the cylinder's volume with respect to the radius, where r is equal to 7 centimeters. So recall our volume of a cylinder formula. The volume of a cylinder V is equal to pi r squared h. Here in this question, we're given that h is equal to 30 centimeters, so we can replace the h in the volume formula with 30. So V will be equal to pi r squared times 30, where V is equal to 30 pi r squared. And notice the volume is in centimeters cubed. We're asked to find dV dr, or the change in volume, so the change in radius when r is equal to 7. So V prime of 7 will be equal to the limit as h approaches 0, the volume at 7 plus h minus the volume at 7 all over h. And notice the h that we deal with here in our formula is not height. This is our change in r. That will be equal to plugging in the 7 plus h into the volume formula, the limit as h approaches 0, 30 pi, parentheses 7 plus h all squared minus 30 pi times 7 all over h. We can factor out the 30 pi from the numerator, so we can rewrite that as a limit as h approaches 0, 30 pi multiplied by all of, if we expand our 7 plus h squared, we have 49 plus 14h plus h squared, and then 7 squared would be 49. So that's minus 49 all over h. So then this becomes the limit as h approaches 0, 30 pi times 14h plus h squared, because our 49 cancel our other 49. 49 minus 49 was 0, so the 49's drop out. So we have 14h plus h squared all over h. We can now factor out the h from the numerator, and so in our next step we have limit as h approaches 0, 30 pi times factored out over h. We left with 14 plus h all over h, and now these two h's will cancel in the numerator and denominator. So we are left with limit as h approaches 0, 30 pi times 14 plus h. Now as h approaches 0 here, we can plug in our 0 for h because now we do not have a division by 0 problem. So we are left with 14 times 30 pi. Our final answer will be 420 pi. Our answer is in centimeters squared. Notice because we've taken the derivative, our centimeter cubed, our volume became, and after we do differentiate volume, we get the formula. Our units will be for area. So that's 420 pi centimeters squared. Now let's talk about something else. So let's talk about the instantaneous rate of change of a position function. Instantaneous rate of a position function, that is, we take the derivative of a position function with respect to time. This instantaneous rate of change is called velocity. So if we're given a position function in terms of time, take the derivative, we get velocity. So the derivative of a position function is a velocity function. The position, let's do this example. The position of an object at time t is given the function s of t is equal to radical 5 minus 3t. Determine the velocity of the object at time t. So again, we said that our velocity was the derivative of our position function. So let us write our position function again. S of t is equal to radical of 5 minus 3t. And so our velocity function, let's call that v of t, be equal to the derivative of the position function. That would be s prime of t. That's equal to the limit as h approaches 0 of radical 5 minus 3 parentheses t plus h minus radical 5 minus 3t all over h. Now notice here there are a bunch of radicals, the minus sign. And remember, if we plugged in our h here, we'll have a division by 0 problem. So we'll have to use one of the techniques that we have learned to sort of simplify this so we don't have a division by 0 problem. One of the techniques we learned was the use of conjugates, multiplying by the conjugates, right? And the conjugate of the numerator with the minus sign would be pretty much the same things, but with a plus sign between them, right? So the conjugate is a plus sign between them. And remember that when we multiply two conjugates together, we get a difference of squares, where it's just the first term squared minus the second term squared. Or if you FOIL it out, you'll get the exact same thing. Okay, so if you have time and you want to FOIL it out, then you can go ahead and do that. So in our next step, we're going to multiply by the conjugate of the numerator. So we end up with limit as h approaches 0, radical 5 minus 3 parentheses t plus h minus radical 5 minus 3t over h multiplied by, in the numerator, radical 5 minus 3 parentheses t plus h plus radical 5 minus 3t. And we also multiply by the same thing in the denominator, which is radical 5 minus 3 parentheses t plus h plus radical 5 minus 3t. Yes, effectively, we are just multiplying the original by something over itself, which is just multiplying by 1. So we are not changing, but we are doing some algebra to sort of simplify it in such a way that we can actually somehow undo or get rid of this division by 0 problem. So that's a limit as h approaches 0, 5 minus 3 parentheses t plus h minus parentheses 5 minus 3t. So this is your difference of squares right here. That's just the first term squared minus the second term squared all over h times, or parentheses, radical 5 minus 3, parentheses, t plus h, plus radical 5 minus 3t. Do not expand the denominator just yet, because we want to, if we can factor out an h in the numerator, to have that cancel the h in the denominator to get rid of our division by 0 problem. So this now becomes, if we expand our numerator and see if some terms will drop out or cancel out, the limit as h approaches 0, 5 minus 3t minus 3h minus 5 plus 3t all over h times radical 5 minus 3, parentheses, t plus h, plus radical 5 minus 3t. So notice in our numerator, a plus 5 undoes a minus 5, and a minus 3t undoes a plus 3t. So what we're left with in the numerator is just a negative 3h. So we have the limit as h approaches 0 of negative 3h all over h, parentheses, radical 5 minus 3, parentheses, t plus h, plus radical 5 minus 3t. And now we can plug in, after the h's cancel out, we can just plug in h equals 0, and so we'll be left with negative 3 in the numerator, and in the denominator 2 times radical 5 minus 3t, and we are done. So that is the derivative of our position function, which is our velocity. Thank you.